什么犯贱？
因为我看到有待过，就是要改，
哦
然后我就是改掉。
，OK。什么？下次跟我讲先，不要随便乱开。
所以我就改了一次，找很少看啊。
哦
要不要？
，OK，later we will discuss about assignment also. Okay, let's start. So assignment. So now it's already assignment 4, right? So we left one more assignment after assignment 5. We will be preparing for exam. Then for midterm. So midterm will be week 8. Week 8. Supposedly we will finish chapter 2 on week 8. Before week 8, before week 8. And so midterm will be on chapter 1 and 2 until the topological stage. So tomorrow is holiday. So this holiday maybe will disrupt our assignment plan again. So hopefully we will finish those steps today. And then I think our assignment just delayed to next Tuesday before the starter. So we will set assignment file also next Tuesday. I mean, not the next Tuesday, but the next 4 week next Tuesday. Okay, no, 4 week, 1 week. Okay, but I'll release the assignment file soon. Yeah, so take replacements, right? When are you guys free? Not free, huh? For tomorrow. Oh, tomorrow. Any evening you free or not? Monday, Tuesday, Wednesday, Thursday. Huh? Tuesday. Tuesday evening. Yeah, Tuesday or you start? Huh? Yeah. Yeah. 啊，4点前没有办，有课啊？Any 5 to 7 slot you free or not? 啊？Thursday? Sorry. All right，这些3到5是 Friday maybe can be earlier. Friday I might whole day free. Huh? Friday when you together. Or how about 2 to 4 Friday? Well, FIP. 讲那礼拜你考试没有见？考试应该就借 FIP 吧？你刚才讲我很忙，因为我要考试嘞。I mean 我 FIP 我全部给他放假。What do you think? Friday 2 to 4. No objection. I'll make the replacement as a midterm exam, so you have to come. Friday 2 to 4. Okay. Make announcement and then see if anyone has an objection. So we will. Friday 2 to 4 weekday. Okay. In that case, we'll continue.
All right, so we speak a lot on the open set, right? Now we're gonna define closed set, and then we'll look at the property of closed set. Yeah. So we'll define a closed set in metric space. Okay. So although last time we speak about topological space a bit already, but let's finish off the closed set in metric space before we venture into topological space. So set A is closed. Okay, if and only if its complement is open. So you might see that a weird or why this definition I put if and only if rather than if. So well, there are a lot of ways to define close here. Okay, and then we will show that they are equivalent actually. And so if you want to replace it as with also can, never mind, up to you. Okay, but the main thing here is we will first define close as its complement is open. Okay, so its complement here, how to write? What's the symbol here you can put in? Pay 是吗？pay, yeah. How to write the complement of it? A subscript C like this. Superscript. Okay, A superscript. Or you will write X Z minus A. Like that. Okay. Other than A is open. So first proposition you're gonna prove is a set is open if and only if its complement is closed. Okay, so how are we gonna prove this? So very straightforward. Left to right, right to left. So first suppose that A is open. Okay, what do you want to show here? Seng, what do you want to show here? Suppose A is open. 哪一个方向？我已经 suppose 了一个方向了，但另外一个方向一定是要拿来真的了。啊？谁是 close？啊 ？complement？什么是 complement？ A B C D E F G A 什么 ？A C OK A C is close OK。but 你要证明 AC close 啊 ，what if you want to show AC close 啊 ，what do you need to show？ 啊 ？What do you need to show 啊 if AC is close？ 问谁？哦，凯旋哈。Its complement is open. So that is AC bracket C is open. But what is ACC? ACC is just A, but by definition is open. By assumption. Okay. Okay or not? You see, what did you see in this argument here? We are not using open here. I mean, not using the open ball condition. Okay, just use definition, complement, complement, complement. Okay, how about the other direction? Suppose AC is closed. Okay, we want to show that A is open. Okay, we want to show that A is open. AC closed means what? Eaten. AC is closed means what? Means the complement of AC is open, but ACC is again A. Okay. So you can see that with this definition, there's no open ball condition you need to use here. Okay, but then what's the relation? Relation back to our open ball stuff and limit point stuff. Okay, so we're gonna prove this next theorem here. Actually, a set A is closed if and only if A equals to A bar. Okay, a set is closed if and only if it contains all its limit points. Okay, so we're gonna prove this. So how are we gonna prove this? Okay, so let's start with one side. A is closed. Okay, A is closed if and only if AC is open. A set is open means what? Last time we say. What is the relation between the interior of A? In this case, AC. AC equals to the interior of AC. Right.
You need to accept yourself first. The leader self.
But what is interior of AC? You can change, right? Bring the C out, right? If you bring the C out, cancel with interior, what do you get? Exterior of A. 外面的里面就是里面的外面哦，对吧？ Is that true? So when you prove these statements, you need to turn into a language that you understand. Okay. But don't do the other way around. Before proving, you already change your language. Because if you do that case, maybe you will get a wrong concept. And after you prove, and then try to memorize it, try to remember it. Okay, try to internalize it with your own understanding. But AC equals to exterior of A means what? This implies that A is in A union boundary of A. Why? Why am I using here? Why am I using here? A, C, and A build up what? 你和你的外面是什么东西来的？就是全世界了是全世界了，你知道吗？你跟你的外面就是全世界了。Okay, you need to remember that X is equals to A union AC. By the same time, we split X into 3 parts using what? Interior of A, exterior of A, and boundary of A. Okay. So if you already know that AC consists of one of the parts of the union, then the other set should be in other two unions. Okay, but what is this? Interior of A plus boundary of A. Last time we proved that this is also equals to A bar. Okay,
So A equals to A.
Okay. Any question here? Any question here? So again, notice here, we didn't use any open ball stuff here. There's no open ball stuff here. Although we define limit using open ball. Okay.
What else we define?
We define interior, exterior using open ball. But if you go through this argument, there's no open ball existing here. No. We just take the property that this interior, exterior boundary will satisfy. That's all. 就这样吧。OK， 没有 open ball 进来这边。OK 了。Okay, one last, should be one last theorem. Yeah, maybe one last theorem that I'm gonna prove to you is before we go to the topological space, the set A bar, the closure of A, and boundary of A are actually closed. Okay, so to show that these sets are closed, what do you need to show? Ivan, to show that these two sets are closed, what do you need to show? By definition. 什么？怎么 study today？我才5 minutes ago 吧。快点，下一念。How to show something is closed? D 排 D 排。Its complement is open. Okay. So if you want to show a set is closed, you need to show that its complement is open. Okay 啊？可以吗？题目哈。哦。OK， 那 so 你要 show that the complement of these two set is open. Okay. So the question is, what is the complement of A bar, and what is the complement of boundary of A? Huh? This is equal to exterior of A. Why? Again, what you are using here? Which theorem? Which equation? 哦，现在的 equation 都是 set 了哦，不是号码哦。对 equation 全部都是 set 啊，没有号码。So what's the equation you are using 啊？啊？ So you need to remember that you can split your set X into interior of A, union, exterior of A, union, boundary of A. Moreover, these union are disjoint. I will prove that their intersections are empty, pairwise intersection. So, did we show what is A bar just now? So we know that A bar is also equals to interior of A, union, boundary of A. Okay or not? So, other than A bar, what do you have? You have exterior of A. But last time we showed that exterior of A is the interior of AC, which is open. Okay. So exterior of A, which is open. Or if you like, there's one exercise, maybe you can show that XA. So let me put an exercise here. You can show that XA is a subset of in of XA. I can try and show this because it's open. Okay. Yeah, try and show this. Okay. So if not, last time we also show you that this is equal to in of AC, right? Okay, so it's in of something. Okay. How about the next one? The complement of boundary. What do you get here? Also see from the X, the decomposition of X. Boundary of complement of boundary of A is just interior of A, union, exterior of A. But we know that these two sets are open. So union of open set is again open. Last time we showed, right? Arbitrary union. Here only got two union. Okay. Which is open as it is a union of open set. Okay. Okay. So yeah. 啊，哪一个？是 open. If the complement is open, open meaning the set is closed. Okay. Yeah. Definition must remember. So A bar and boundary A are closed. Okay. Okay, let's give some example of closed set here. For example, is this closed? Okay, so can you just write it as interior of A union boundary of A or not? What's the interior point? Interior point means what? Every point you can build a open ball around it. So what's the interior point here? Open bracket from A to B. Okay, you can check that every point inside here, you can build a ball within the interval. How to build? You need to find the minimum distance between point X and the endpoint A and B. Okay. And then the boundary point is just A and B. Okay. Okay or not? Because why? If you pick other point than A and B, what happens? You can find a open ball around it that avoid this set. Okay. So they are in the exterior of this set here. Again, empty set and Rn are both closed. Okay, don't say Rn, the whole space are both closed. Okay. What else? There's something that's not open and not closed also. For example, the rational number and the half open interval are neither open nor closed. Okay, maybe you can discuss. Let's discuss about the half open first. Why is it not open? Open. Huh? Open more. I. Huh? Sorry? B. Point B, what happened to point B? If you build any open ball around it, what happened? You cannot make sure that this ball lives entirely inside the set. Okay? So there's a point in the set which is not the interior point. Yeah, which is not the interior. Why is it not closed? Okay, let's not use the sequence language here. Use the language we introduced. Boundary limit point or what? Hey, have we discussed what limit point is? How do we introduce limit point? Oh, we did introduce limit point. Okay, so can you like say why is it a limit point here? Using our limit point definition. I think it's related to sequence, but we use the ball language, right? Yeah, it is related to sequence because what's the definition of limit point? Every open ball around your limit point, there exists another point that's not equals to, okay, in this case, A, but it is in the set of, it is this half open interval. That other member here become your sequence, your MA1. Okay, now we're going to use the ball concept here. So in other words, this A is what? It's actually a boundary point also. Right? Because no matter what ball you build here, you're gonna intersect the complement of the set. Okay, no? Okay. Yeah. Again. Okay. So no matter what ball, open ball you take at 8, you're gonna intersect the complement of the set and the set itself. Can you imagine or not? So when I draw this interval, you should have some picture in your mind. So you got A here, you got B here. Okay, you take a close and open here. And no matter what open interval you take here, you're gonna intersect open interval and the complement of open interval. 对吗 ？Is this what boundary means？ 过来一点就出去了，过去一点就进去了。Okay. But this boundary point here is not living in this set. Okay, just now we show what? A has to be equal to interior of A union boundary of A, so that A is closed. 记得吗？刚才我们说的 A must contain all the interior point and the boundary point. But we found one boundary point which is not in the set. Okay, so it's not closed. 对吗 ？get 得到逻辑吗？有人不见吗 ？Okay, so bear in mind if you want to show that a set is closed you should contain all your interior point and your boundary. Interior. Okay, so can you use the same logic here to show that rational number is not closed and not open? So what do you do? If you take any point in rational number, make the ball, it will contain irrational number. Why? Because irrational is also dense in real number. Okay, so you will find something in the complement of Q inside the ball. Okay, so this shows that it is not open. Close it. The boundary, what's the boundary point of this Q here? What are the boundary point? Boundary point definition is what? Every open ball you make, it will contain point inside and outside. In particular, rational number is a boundary point or not? Yes, right. Also, yes, right. Because you build a ball around your rational points, it also contain rational point, irrational point. Right? It's a boundary point. What else you could ask for? So in this case, you need to ask where my Q sit in actually. Sit in where? Sit in R2, sit in R, or sit in where? Okay. Usually we'll assume that this guy will sit in R. Okay, so if we discuss about R, so we need to ask whether the other points in R is a boundary point of rational or not. So what are the other points than rational in real? They are the irrational. Okay, so you go to the irrational, build a ball around it. Does it contain rational and irrational or not? Yes. Why? Because irrational is also dense in real number. So irrational are also the boundary point. But the boundary point, the irrational are not in the rational set. So it is not close. Okay. Make sense? Okay, ma. Okay. Okay. So look like this. You see, my notes maybe looks like this. However, what I say, right? I just said it out. I didn't write it down. Okay. So, a very good practice is go back and write it down. And actually, I want to do this in the lecture notes. So I have been asking Zhao Seng. Everyone know Zhao Seng here already? We went to Mamat last week, right? And not Mamat, Maggie. Zhao Seng, this pink guy here. So Zhao Seng, I asked him to like build a solution, empty solution link to all these arguments that can be filled. Okay, so if you are willing to, you can contact him, write the solution down, full solution down. I think he make a Microsoft form which I can share to you. Then you can input your full argument into the Microsoft form. Okay, so if you help him to type these things out, then it will help you to study this course also. Okay, it's equivalent you doing revision for this course already. Okay, okay, ma. Especially the 2304 batch 配合做一下你们，好像你们两个 batch 可以互相学习，你们两个 batch 有不同的优点，我们可以互相学习。2309跟2309，哎，这你们是同年的对不对？你们是同年的好像，
而全部属猴的，对不对？他们属猴然后呢，我觉得你们可以多一点认识对方，互相监督。
宇宙老师
啊，
宇宙老师，
做好吗？Yeah. Okay. What's next? It's already 10:30. Good. Good timing. Okay. Next part will be if you take a bunch of closed set. Hey, also another thing is master. Master also can help. Last time, you know, the general topology is typeset by Wen Chuan. You know Wen Chuan? Yeah. He got A in general topology. I don't know if there's a direct relation, but for sure this is one of the reason. Okay. Yeah, so he can try to how to say organize the idea. Yeah, organize the idea. In particular, he found a lot of typo in my notes actually. Yeah, for sure. You need to be able to find typo to prove that you understand, you know. If you don't understand, you don't even able to find the typo, you know. Okay. Okay, so if you have A1 up to AN are the closed set, then A1 union up to AN is also closed. Okay, it's also closed. And what? And if A1 is a bunch of collection of closed set, I don't care how big is it. Then the intersection, then the intersection of AI is also closed. Okay, let me ask another question again. How to show this set is closed? 把你打乱了，再回来问你，来问谁？Ian, how to show that these set are closed? So that the complement is open. So if you take the union, the complement of union, what do you get? You have to show that the intersection is open. Arbitrary intersection after taking complement become arbitrary union. But this is a statement we already have for our open set. Okay, not. So this result actually just follow from De Morgan's law, and the result we proven for open set, where finite intersection of open set is open and arbitrary union of open set is open. Okay, or not? So we turn the result from open set to closed set using De Morgan's law. Okay. Okay, so this one just follow from De Morgan's law. Properties on open set. Okay, so if we collect all these together, we have this ultimate theorem for metric space. Okay, so what do we have here? Theorem in a metric space. So I want to emphasize the metric space here because later we won't see a metric space anymore. So in a metric space here, A, empty set and X are open, finite intersection of open set are open, arbitrary union of open set are open as well. Okay, we have a dual statement here. So let's say A prime. Empty set and X are closed. Finite union of closed set are closed. Lastly, arbitrary intersection. Arbitrary intersection of close. Okay, here close set are close. Okay, so this is the reason why we jump to topological space. Okay, so this is the essence of metric space. In fact, from here we can already build the limit point, the compactness, the completeness, connectedness that you want in MA. Yeah, just using this, either open set or closed set. Okay. Okay, so let me mention a bit of history of topological space here. Just very brief one. Let me mention a few person names. Where is it? Okay, so there are a few person very prominent figure here. One of them is called Fraction and Hausdorff. We're going to see the definition on Hausdorff later. They try to propose a different definition, okay, over a period of years, during the first decade of 20th century. Okay, so you can see that the theory you learn is built across year. So if there's a student tell me that, oh, I want to master it in this 3 months here, I think you are crazy. I mean, the sense that you want to master lah. You said it like very ideally, oh, I want to master it. Sorry to say, until this day, I still haven't mastered it. You get what I said? We are learning every day. Learning process is every day. It's not like one period done, not like that. It's continuous one. You are Chinese, right? You should know a phrase, 温故知新。不可能温故知故的嘛，对吧？温故知新。Keep changing, like refreshing your knowledge. Okay, so what do they want to propose the definition for? They want to propose a definition that could include Euclidean space, infinite dimensional Euclidean space, and also the function space. Okay, so they come up with topology enough to cover all these spaces, to study all these spaces at one go. Okay, which is the topological space. Okay, no. So like last time we say, we just call the member in the set as a point. No matter it's function, it's a factor, it's a number, we could just call them points. Okay, because we try to give this abstract definition called topological space to include everything inside here. Okay, so that we can discuss at one go what property they can satisfy. Okay. Okay. All right. All right, so we're gonna define topology now. So finally, we reach to the word you see in your course name, topology. So what's the topology here? So let's define. What's the topology? So this topology, you should start with a set first. Okay, so we define a topology on a set. Okay, but what is it? It's again a set, a collection. Usually you see the books say tau for this set here, not the topology. Tau, a collection of what? It's really set theory. It's a subset of X. Okay, so meaning what? This collection here, all the elements actually are the element of the power set of X. You just group a bunch of things together, okay, from X. Having what property? Having the following property here. First, you must pick the empty set and the whole set in your tau. Okay. What is a topology? Topology is a set. Okay. Inside this set here must contain empty set and the whole space. Correct or not? Empty set and whole space is a subset of the whole space, right? Okay. In particular, they are the element of one of the elements inside your tau set. So I can choose them. Second, tau is closed under finite intersection. Okay, so meaning what? If you have other set inside tau, make sure that if you take finite intersection, it is still inside your tau. Okay, it's still inside your tau. Other calling. Wait, let me reply this. Okay, and then third, tau is closed under arbitrary union. Okay, so for example, if I is an arbitrary index set, no matter how big, so that's why we settle the problem of countability, uncountability. So here doesn't matter how big is it. And if you take all the UI from tau, the whole union should live in tau again. Okay. So what can you see here? So here we are mimicking the open set in the metric space. We are mimicking. 我们要反照那个 open set 在 metric space 里面。So if this happen, then the elements in tau actually are called the open set. Okay, and then we will define that a topological space. Okay, so topological is an adjective, right? So space is another thing, right? So there are two things inside this word here, space and topology. So meaning what? This is a pair or tuple. Bracket X and tau, such that X is a non-empty set. If it is empty, very boring. Okay. And tau is a topology on X. So meaning what? 有没有人可以总结一下什么是个 topological space here？总结一下。来洛星要不要试一试？不要。哇，这么果断的拒绝我，好。找一个嘉怡。Can you try to summarize what is a topological space is? Right? How do you start with? What do you start with? What do you start with? A topological set. Sorry, topological space. What do you start with? 用什么开始？怎么开始 ？Yes, good. 用一个 set. And then, what's the topology? maybe 要不要拉上去一点 ？What's the topology?
Collection of subset of X。OK，什么意思啊？这里什么意思？啊，游泳。So topological space 是什么？是一个 set 的一堆的子集，用华语来讲的话，谁的子集 ？X 的子集。可是你不可以随便选哦。You cannot simply choose these subset. This subset has to satisfy the three conditions here. Okay, so you need to make sure that you choose the empty set, choose the whole space, and then the set you pick, it is closed under finite intersection, closed under arbitrary union. Okay, now, and then we will call this open set. 就是这样定义的，让它 open。Okay, now. Okay. So topological set is some set with its open set. So when we say open set, open 会 cover 这些 property 啊。Okay, now openness will cover these property here. When we say this set is open, oh, you will know that it is closed under finite intersection, closed under arbitrary union. Okay, now, and then empty set and the whole set is there. Okay. Okay. Similarly, 我可以转一个方式嘛 ？Can I define a topology such that T is closed under arbitrary intersection and closed under finite union or not? 可以吗？我可以这样定义吗？ If I define like that, then we will call this set as a closed set. Because closed set in metric space satisfies the other relation. Yeah. Yeah. Okay. Actually, these are two equivalent ways to define a topological space. Okay, these are equivalent way to define topological space. Okay, so if you define an open set topology here, it will already give you a closed set topology. Why? We can declare that the closed set is the complement of open set. Later we'll define again. Okay, later we'll define again. Okay, so this is just something that I want you to think about. Later we'll define properly what's a closed set in a topological space mean. Okay. Any question before we take a break? Okay, if no question, let's break until 11 o'clock. Ah, 我自己带水。没啦没啦，不是这个是上面。 我知道为什么，而且为什么？不可以，不可以。你注意我。会再去，
没有这样。哎，咋了？
请我就去，然后去玩。
哎，
我觉得我们是找一个 paper 来 study。
你都可以找，但是你要找一个题目是来那个地方不是 topology，但是它会用到 topology。
OK OK。
So yeah，I mean quite broad 啊，你要到 physics 也是 OK 啊。
哦，
但是我们先讨论看一下是不是
OK。哦，所以是一个 topic 罢了，然后要不要用到其他 paper 是
depend。
哦
depend，都要用几个 paper 都可以。
OK。所以就是我自己定了一个 topic。OK。
啊，就是它的 point 就是来你去其他的 field 到 topology，
到头回去 OK。
要到 topology。I mean 你是 physics background 是不是？啊，你还是啊，可以 try， 可能选一个当然会来。
可以啊。
找了。哎，
没有，你没有黑板的样子。
看不到，找人电话。
这个可以试一试。
就是这种组织的。
但是我从来，可是我是看不懂啊。
你解释，你可以
你这样说哦，它是用function for 来 x 或者 x，然后你呢？
你没有 define， 你有没有 define 那个符号上？我们班上有没有讲？
我觉得他没有，我觉得你们
你应该是要用一些。
他肯定有，
没有什么来了，那什么来了？
然后我觉得还是
对啊，你都不知道，你怎么 expect 我知道？要每个人讲不知道的东西，我怎么会知道？
你不是老师吗？
我不可以这样知道，这样的话我什么都知道。你不用做啊，
还有，
不是没有选择。你想想，你是数学家，你想看这个逻辑在自己想。不现在你的讲的就我什么都会啊，这样你还要写，你不用写啊。想想你自己想的。
因为没有我的数学的意思，你学的比我们来多。
对了，我就讲了，如果我什么都会啊，我放大一点。
但是你刚刚说的是他不会的，你也不会，就显然错。
没有，因为我用三角这是就我的，
这个也是对的，因为我开宗明义告诉你啊，我有东西不会。
对啊，
我不是什么都会啊。
刚刚那个对他不会的，对，有没有人来做那个？
没有，因为正常你读这个东西哦，你是要以不会的去读你才能，然后主要你不会一下，所以我少一个东西，我少的东西谁没有写，可是因为这东西是之前的课教过，在Topology教过，所以他就讲说这那里的他是不会吧。
有没有跟读的一样？
有没有看出来？
不要走小道就是了，我只给你一个 principle， 不要走小道，什么东西就清楚写下来，因为你这种小道你放在其他工作上面啊，这些全部都会出问题的，一定会出问题的，问题都是从这里出。跟从者就觉得说你讲的不止。
我还是不懂为什么
如果他们他不懂去那边解释给他们。
他其实要讲的是那个左右的厘米。
哦。
他要讲的是左右的厘米不一样，不一样的话就有个距离出来。明白？哦，它是discontinuous 就是它左右的距离那个厘米不一样，它一不一样，它就有一个距离出来，一个 open set 跑出来，然后你就可以从那个 open set 里面选一个 reference。等一下我们OK 啊，
还是没有写红色吗？
礼拜四可以看晚上吗？
那我不懂，晚上我而已。晚上你是明晚上要来吗？
来什么
？Orientation next 10，你来玩？
没有空。怎么拜四是放假？怎么你们放里面在拜四？
没有，就是我们定这个时候，我没有想的是老东西，解出来反正。
然后你们这么一直 tag 我，然后又不见 tag 我又不见，你们一直 tag 我那个 story， 然后又不见 tag 我又不见了，我不知道你们到底要不要 tag 我。
写错的。因为那 post 一次我看到授权，我就马上删掉，我就跟他讲，你会看到删掉过后，至少要过一段时间。
Okay, let's start. So let's give some example on a topological space. What's the first examples you know of topological space? We've been discussing for the past weeks, right? What's the first examples you know? If X is a metric space, okay, how is it a topological space? What are the topology you can choose here? What are the topology you can choose here? What's the topology you can choose here if X is a metric space? Open ball, huh? Okay, so these are all not just the open ball, the open set. Okay. Open ball actually, yeah, open ball. The collection of all the open balls. The open balls here, so is the radius here, is actually a topology on X, which is called the metric topology. Okay, so whenever you heard the word about metric topology, meaning what? You take your metric, form your open ball. Okay, and then these are the open set. Okay, generated by D. Or sometimes we will say that this topology is induced by the metric. Some of you asked me in the past assignment, right? What does it mean by induce? What's it induce? Okay, so if A is induced by B, meaning you want to use B to define your A. Okay, your A comes from B. Induce. Okay. Induce. Okay, so in particular, if you consider the Rn, right? The Rn in your MA1, this is called what? This is called, in your MA1, your subject is just Rn with the topology here. Is the n-dimensional Euclidean space with the Euclidean topology. Okay, this is the only thing your MA1 learning. MA2. I mean, the second part of your MA2 maybe is a bit differential geometry. So it's kind of a mix between geometry and topology. Okay, so this is the very first examples of topological space. Okay, now we're gonna play a little game here. Let's define topologies on 3 element set. So let's play this game here. This game is kind of combinatorics. So let's say we just have 3-point set here. Okay, 3-point set here. So how many topology we can define here? So let me give you one of the topology, which is called the trivial topology. Okay, meaning we just say that, oh, the whole set and the empty set is open. Is it closed under union or not? Closed under intersection or not? If these two happens, is this set closed? So okay, so let's say this trivial topology here, or call it what? T trivial is just X and empty set. Is it closed under union? Is it closed under intersection? Why? Because if you take union, you go back to X, take intersection, go back to empty set. So it's closed. Perfectly good topology here. Okay. Maybe let me try one more, then I will let you try. Let me try one more. What if I declare these sets are open? Okay, so what do I mean by I declare this set to be open? So this topology 1 here, we have whole set, empty set for sure. You cannot run away. And then what else? Just now we summarize, right? Topological space is just declaring some subset that you want to choose to be the open set. Okay, so if I draw like this, meaning what? I am taking the subset containing A and also taking the subset containing AB. That's all. Okay. So can you check whether finite intersection holds or not closed under finite arbitrary union? So these two are quite non-trivial, right? So if you intersect them, what do you get? A union them, AB. Okay, and then you can do other intersection as well. Everything intersect with empty set, you will get D. Union with empty set, you get back the other set. Then you can play around with X. X intersect with all these sets. Either you get A, if you intersect. Okay, if you intersect with AB, you get AB. If you intersect more with A, you get. You union everything, it's just X. Okay, so you can check all these. All right, so I give you 3 minutes. Try and pick different subset such that they form a topology using these 3 points. Okay. The answer is there are 9 of them. See if you can find all 9 on them. 9 of them. Okay, yeah, I give you 3 minutes. Try check what topology you can define on this set. So these two are different topology, so meaning there are two different topological space. Okay, there are two different topological space. So one is X trivial topology, and then the other is X with T1. Okay, so there are 7 more. Try and define. Try and write it down. Huh? Try and discuss. You can discuss with your friend. When I say 9 of them, I'm equating this type of topology also. We don't care about the permutation of the point. Okay, so we regard these two topologies the same. So we said there are 9 types of them. Okay, so we don't really care about the permutation of. Then we should have 7 more types of topology. Okay. Regardless the permutation of the vertices. Okay, try and do 7 more types. Yeah. You must draw it out. Try and draw it out. It's very visualizing one. 很形象化的，你一定要把它画出来。Yes, first topology, second topology. Okay, so once you draw out a topology, right, ask yourself, is this a topology? If not, you need to show to yourself which rule get violated. Okay, 为什么它不 close under arbitrary union？ 为什么它不 close under finite intersection？ 你要 show 给你自己看。Okay， 你要会 show。Okay, let's try. So you see, we have trivial topology, right? We actually can go the other extreme. The other extreme says what? Means what? We actually can declare everything to be open. 每一个东西都要 open. Every element must be open. 每个东西 here means every element must be open. In this case, what does it mean? You will have all the power set to be open already. Okay, it's because you need to be able to take arbitrary union, right? So if I union the third one and the first one together, first one and the second one together, and then second and the third one together. Okay, this is what we call the discrete topology. Okay, discrete. Because we declare every single element to be open. In this case, if you take arbitrary union, then you will get all the power set actually. You get all the power set. This case here. 我来讲，不懂，不是一个，是每一个。我们定义的 topology 是 we define one, we declare， 我们让它 open。你知道什么意思吗？就是 like go back this definition a topology is a collection of sets. So when we define a topological space, we need to tell you need to tell me one. 什么是 topology? What is this collection of open set you need to consider? 懂那个逻辑是什么意思吗？ Topology, what is a topology? 重复一下。来，放上去。 What's the topology? Subset of X 对 ，but 不是随意的 subset of F 哦。Subset of F must satisfy 这3个条件。Okay, such that 这个 collection 里面 must contain the empty set and the whole space. And then once you have any set inside your topology, then it must be closed under finite intersection. 有点像 group 啊，还要 close under multiplication， 这边要 close under finite intersection， 还有一个 close under arbitrary union。只要这些东西在里面了，这些组合都要在里面。So the third topology we are doing is first we pick all these singleton set to be open. So meaning I include them into my topology first. 我把它们加进这个 topology 里面。过后有2种可能性嘛，它的 arbitrary union、finite intersection 都要活在这个 topology 里面。OK， 懂什么意思吗？啊，没事就问吧，因为你卡的地方应该也是大家卡的地方。我们先找到它有哪些 subset。这句话可以再清楚点的，因为 subset 反正我们知道，我们哪一个 set consider 到 power set， 全部 subset 我都知道。Yes。可不可以 form 一个 topology？ 如果它 form 一个 topology， 它是怎样的 topology？ 什么是叫怎样的 topology？ So if you consider here, how do I build this 2 topology here? The first topology, I only first choose X and empty here. And then this is enough to form a topology. Because already closed under finite intersection, closed under arbitrary union. OK 了，已经 close 了这个闭环了，闭起来了。But 这个呢 ，let's say for the second one, let's say if I don't pick the set containing AB, is it still a topology or not? Still. 好像 yes. We found another topology. Wait. Let me see. Can we make this not a topology or not? Actually, it's still a topology. Actually, we managed to create another topology. But wait. Okay. So then this is not a good example for raw Seng then. How should I give another example here? 拿这个 OK 拿这个 So let me write this down first. So what's the topology here? The topology here includes S empty set, and then A, B, C, and then AB, AC, BC. Enough. 2 to the 3, right? 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay. So if I remove, let's say I already declare this 3 singleton here is open. Okay. Can I not include the set in containing BC or not? To be a topology, you need to close under union. So if you take the union of B and C, you have to live inside the set. Okay. You need to do this process, repeat this process until you get a closed set. 让它停止为止。Terminate. I mean, the word is close. Is what the close means. 不是。We are abstracting the concept of open. 就是这个 ultimate theorem 这边。那些 open ball 之前那些 open ball 符合这些条件。现在我们只看这个条件，我们不看那个 open ball。OK 吗？OK 吗 ？Yeah. So this is the difference between metric space and topological space. 因为 open ball 了，我们就 open set。什么叫做 open set？ 就是符合这些条件的东西，我们叫 open set。OK 吗 ？Make sense? Very important distinction here between topological space and metric space. 我们没有距离了 ，there's no more distance anymore. 没有尺了哦。 没有词了，词音 ，topological space 里面没有词了啊，没有词，只有开放吧？Yeah，开放，不是吃饭，open，OK，没有词了，OK，适应饿了，感觉适应真的饿了，OK，so you see 啊，just now 哦，我们不小心好像造了另外一个 topology 出来，用刚才那个情况。啊，如果我们把这个 AB 丢掉哦，还是 still close under this operation。Correct or not? X union A singleton A, empty set union singleton A, intersection between singleton and all these set is still circulating around these three sets. Does it make sense? So you actually build another topology here. So what does this topology looks like? So you just circle one set here. So this is the topological, the fourth topology here. Okay, where you just include one of the singleton set. 还可以做一件事情，对不对？刚才我想丢 A 也不行哦，这样把这个丢掉还 OK，still close. If I just throw away the singleton set. Okay, so there's another topology, the fifth topology, whereby you just take an extra subset containing two points here. Okay. 还有其他的 topology 吗？ Anyone draw other topology different from these five? I said got 9, right? Still got 4 more. 有人画不一样的 topology 出来吗？哪一个？两个中间一个 try 啊。So this one is 第5个 ，this one is 6. A B C 两个是怎样？这样两个眼睛，中间再加一个眼睛。Okay, still a topological space. You can prove it. Okay, 你可以 try and prove it. Go through 所有的那些 closeness. Okay. What else? 还有吗？还有3个。还有3个。还可以讲话眼睛。还有什么还没画出来？一个跟2个，这个画过了嘛？刚才是大的包小的嘛，大肠包小肠。现在是一个猪鼻子，一个眼睛。还有吗？讲一个一个。哦，就真的是猪鼻子，这样子。OK，and then 还有一个是 you can use topology number 6 and then include one more point here. Okay. Yeah. Okay. So try and prove these are the topology you have. Okay. How about I check whether you know or not. So let's give a non-example here. Let's check a non-example here. So let's say I just declare the extra 2 subset to be open. I claim that this is not a topology. Why? Right? Why? This is not a topology. Why? Sorry? Not sure. What should you think about first? You need to think about finite intersection and union. So can you take any intersection here such that the intersection is not the thing that I declare as open? Yes. Correct. So what does it mean by B? So meaning I need to pick this singleton as open also, but I didn't choose it. Okay. How about I give you another example? If I take these 3 points and I declare these two singleton to be open, this is not a topological space as well. Why? Joshua? Why? There's really two operations you need to think about: union and intersection. Huh? Arbitrary union. Yeah. To be open also, right? But this guy I haven't included. Okay. The set containing these 2 points.二十一点 intersection 不应该是 open 哈 ，open 谁的 intersection 不在里面？谁跟谁的 intersection has to be closed？ 讲好来，哪里在哪里？哪一个 definition？ 这个 ，where？ 这个哦 ，you confuse this closed word and the open。哎 ，careful 啊 ，you careful 啊。This close is not the open and close 啊，这个 close 是怎么说呢？这个 close 这是 like the group definition 啊 ，close under addition， 就是说来有一堆东西，如果你做了一层的做还在活在那个 close 上面。Yeah, so you have to be careful 啊，要小心一点啊。Yeah, this close is not the open close thing 啊。Yeah, 要小心啊，要小心啊。Okay, so this is close under operation. Close under operation. 之前那个 close 就 close 完了，那就是一个 open close close。但是这个是 close under some operation。OK， 小心啊！有人会犯这个错误的，所以大家要小心一点。OK or not? Everyone happy with this non-example here? Okay, so the question here you can try. So there's a question here. So can you figure out in general, how many different topology you can put on n element set? Now it's just 3, right? So now do it for ON. So this is kind of like a combinatorics question. Okay. Yeah. So for 4 points, right? How many types you can draw? Okay, up to permutation. Okay, we don't want to care about permutation. Okay, how many types? 5, 6, 7, 8. Any formula or not? Got formula or not? And maybe we can make this into a FYP problem actually. Okay. Yeah. You can think about how many topology you could have. Okay. Okay, let's continue with examples of topology. What else? So let's continue. Let S be a set. Okay, let S be a set. And then first we could define a discrete topology. Okay, so just now I already disclosed to you what are the discrete topology, meaning what? You declare every elements in your power set to be open. Okay, in particular, all the singleton will be open. Okay, so you make it discrete. The other one is called the trivial topology, or sometimes you'll see that it is called the indiscrete. Okay, indiscrete topology, meaning what? What are the only open set here? Just take the whole set and the empty set. It's indiscrete, right? 你看不到里面有什么的，就有还是没有吧？就整个就没有，或没有。你看不到里面是什么 ？You cannot see things inside， 看不到 indiscrete， 全部揽在一起了。Okay, everything is the same. Okay. Two more very important, not very important, but very interesting topology here. So first is called the finite complement topology. Finite 又 complement 是什么意思哈？ Finite is a set to be finite 嘛 complement is also a complement of a set. So sometimes we call it a core finite topology. Actually, we met this topology in algebraic geometry, right? The Zariski topology. So what's a core finite topology here? Let X be a set. Obviously, we have to start with a set for topological space. So what are the set we declare open here? So let's call it TF. These are all the subset of X such that X minus U. So the complement of this set should be finite. Okay, should be finite. Or the complement of this set is just the whole space. Okay, so meaning what? We want this relation to hold Y because we want to include the empty set into it. Otherwise, if X minus empty set is what? X set. If X is infinite, then you GG. Empty set is not in here. Okay or not? So that's why we add the extra condition here. X minus U is X. So that we can make sure that our empty set is inside here. Okay. Obviously, the whole set is inside here, correct? X minus X is empty. Empty, what is the cardinality of empty set? I think we define it to be 0, right? Yeah. So 0 is less than infinity. Okay. Okay, so this is one of it. Next one is the countable complement. Or we call it a co-countable topology. Not coconut topology, co-countable topology. Okay, so what's a co-countable topology here? 来猜一下什么是 countable complement. I already tell you what the finite complement means, right? So try and guess what's a countable complement mean. Can you mimic? Try mimic. 它的 complement cardinality as large as n. As large as n. N what's that? 妈讲嘛？你讲嘛 ？L left not D as large as n correct or not? Does countable means as large as n? Can also be finite. As large as n means what? It is denumerable. Okay. So countable include the case where it is finite. Okay. So this cardinality should be countable, or again, we want to have X minus U to be X again. Why 来 test 一下，正月，为什么我们要有这个 extra condition？ 为什么如果没有放这个 empty set 可能会在外面？如果 if X is uncountable, then X minus empty set will be uncountable. Then 它就不 countable. Okay. And then last definition I gave you is given topological space X and tau, we'll say that a set U in X is open in the topology tau if U is in the topology. Okay. Only the thing that we say that is open, if it is inside this topology, we'll call it open. Okay, so after today, inside your mind, open set is no longer containing open ball. It's just a bunch of set that satisfy this three property here. Close under finite intersection, close under arbitrary union, and then empty and the whole space is open. That's all. 就这样，没有 open ball 的。Okay, for topological space. Any question or not? Any question? 原题吗？ Okay, I think the topological space, we will stop here first. We could discuss about assignment. For these two assignments, I think you guys are doing quite okay. The result is about the same, 84% average. Last time we saw the high scorer for this time is Larry, Adrian, 49, 50 between that. Eric, Rachel, okay. And then last time we got more. Last time we got Dong Jie, Larry. These are the full marks. Eric, Zhao Shen, Rachel, Zheng Yue. Okay. So when I mention all these names, 我不知道你们分谁是天才不天才。I want you to learn from them， 互相学习。Okay. In fact 你们全部选我课的都是天才你知道吗？你们都是天才，你知道吗？他们不敢选我课，你知道吗？就连老师都讲你教这样难看有几个人要选你的课，所以我要谢谢你们我真的要谢谢你们来拿我的课你们做好来，我一定给你4.0我尽量，我尽量，真的，我尽量。他们讲我很狠心，之前我一定做了，我能做我一定做给你了。但是你不要说我没有做功课，我又不要交功课，我又不会，我讲给你你讲是吗？你如果是老师的话，你给吗？是不是不给？是不是实营？对不对？我就是看得起你，因为你就是兵班教练。那你可以这样子给兵班学员过是不是？打出去打没有名额，不会拿名额这种球员，对不对？是不是？明白吗？ So you have to come to my office hour. Okay, if you don't understand, you must come. Okay, you must come. Okay, you must come to my office hour. Okay, 我保证你会你做2个星期的东西，我保证你在2个小时内做完了。你来，你一定要来。OK 了，你一定要来呀。去年就是他们班2309Abstract Algebra 天天来，每个星期来。拿 A 拿 A 减你问一下他们在其他班拿什么分？小于等于 A 减，好不好？他在我班是 A 大于等于 A 减，好不好？明白吗？你一定要来，你一定要做，你一定会的，我保你会，不可能的，不可能你不会的，你明白吗？你一定要来。Does it make sense? Okay. 好 ，Yeah. Okay. So let's discuss about the assignment. First question is show that for any irrational number here, x, there's a sequence of rational numbers R1 that converge to x. So a lot of you, there are a few ways. One of you use the decimal expansion. Right? You use the floor of the power of 10, right? To show that it's closer. But one thing about that step, you need to argue why the decimal expansion get really close to your irrational number. You need to argue that. If not, you just use the density. Okay? How do you use the density here? You just create the interval that is closer to x. How close is it? 1 over x. 1 over I each time. So you E over N 越来越小。Okay or not? Okay, use the density to prove it. You can go very MA on this question, or you just give a less rigorous stuff also can. Okay, I will give you mark. If in case I don't give you mark, you come and see me. We can discuss. And about the decimal expansion thing, make sure you are aware of this infinite string of 9. Make sure you are aware. Try to include this argument into your step. because sometimes you will have some ambiguity, okay, in your argument if you don't discuss infinite line. Okay, and then part 2, some of you will use axiom of choice, right? Because maybe you think that got infinite choices to make. But if you already actually there's one choice, one specific choice you're gonna make in part 1 already, you can just use part 1. Okay, but if you want to pick a random sequence, up to you, you can work it out also. But the thing is, you want to show it is injective. The math is injective. I still got like about 2 students are still confused with injection. How to show f is injective? It's not x not equal to y imply fx not equal to y. It's the other way around. Start with fx. Wait. Sorry. Sorry, I confused myself. So you shouldn't show injective using x equals y implies fx equals fy. Okay. This is about well-defined. Yes, good. Okay. So you should start with fx equals to fy imply x equals to y. Or you start with x not equals to y imply fx not equals to fy. Because this is the contrapositive statement. Okay. Okay, don't confuse. Don't confuse. Okay. So another technical part here is this. So once you send your irrational number to a sequence, right, you want to show that this is injective, meaning what? These 2 sequences cannot converge to the same limit. So some of you just use that, because the limit of the sequence is unique. Okay, it works, can. Okay, but here I choose to put down the epsilon the epsilon argument here. Why? Because in the later course, you will see that the limit of a sequence might not be unique. Okay, if we change the topology, it might not be unique anymore. For example, for non-Hausdorff space, for example. Yeah, so what's a non-Hausdorff space? You'll see later. Okay. Sequence, limit of sequence might not be unique anymore. It's just you live in Rn, it is unique. That's it. Okay. In future, no more. There's no unique limit of sequence anymore. Okay, in different spaces. Part 3. Part 3 a bit tricky. Part 3, you want to show that the cardinality of power set of Q is C. So 2 and 1 give you one direction already. So you need to show the other direction. Okay, so the other direction you can build using the power set technique. So power set means what? You can decide whether an element is inside this subset or not to build your sequence. Okay, to build a sequence. This sequence actually I put it in decimal. Some of you put it in tertiary expansion also can. As long as you can differentiate this sequence, it's fine. But some of you just use that 2 to the power n, 2 to the power the cardinality of n is C. This is actually what this question asking for. So you cannot use it. Okay, so actually you need to prove it. Yes. In our class, we didn't really show that power set of a set is the 2 to the cardinality of that set. Actually, you can show that also using this technique also. Okay, also using this technique. Okay, but you cannot say that 2 to the cardinality of n is C because this is what this question asking for actually. Okay. Okay, 2. Wow, 2 a lot of you use stereographic projection, very pro That one is the thing in differential geometry. 是不是上网跟你讲的？没有啊？哦，RS 讲了哈。Very pro，不用走到那么远的 ，no need。Why? Because S2 already a subset of R3. You already have one-sided injection already. How about the other side? You just need to inject a set that is as large as C. So what is as large as C? You just pick this. Okay. So this is a sphere, right? So let's draw the sphere first. For the other direction, you just pick this sphere is enough. This equator here, not this sphere. This circle here. Okay, because this circle here is about as big as 0 to 1, interval 0 to 1. Correct or not? right? So this is the parametrization you can use here. Okay, this is the parametrization you see in calculus 2. Okay, so the height is 0. Okay, the height is 0. So why is it the height is 0? This sphere, what does this sphere give you? This is a unique sphere center at the origin with radius 1. Okay, so this is the unique circle on the, we call it equator. Or there's one very interesting way to show it. This is done by Larry. You see what Larry do? Larry first put this S2 into a cubes. Okay, so we draw this. So this argument, all these argument is very visualized one. You should draw it out. So first what he do is he put this sphere into a cube first. Okay, put this sphere into a cube. Okay, my cube is like 2D. So let's draw 3D. And then make this cube into a smaller cube. 变短嘛，0到1的 cube. So where is the 0到1 So maybe somewhere around here 啦。OK， 变成一个小的 cube， 大的 cube 跟小的 cube 一样大。Larry 讲，没有一样大啦，就还更小，还更小 ，maybe 更小 ，maybe 更小。We haven't shown projection 嘛，so maybe as large as large. I cannot say that. Okay. For this large box here, sit inside this small box here, and then small box 把它边边去掉，把它边边去掉 ，open， 把它让它变得 open 掉，把它边边去掉 ，and then 原来你的 box 跟一条线是不是可以放进一条线里面？你把你的 box 丢进一个线里面，一个 interval 里面 ，and then 再把这个 interval 丢回你的 X 里面。Okay, no. So this is what all these injection are doing. Okay, yeah. Okay, yeah. But I have a request. Actually, some of your solution could be shortened. 可以再写短一点，写精简一点。OK， 你看我答案只有3面吧，不要写这样多，不用写这样多。如果 if you have some detail you scared whether you want to prove it or not, you can come and ask me. I can let you know. Maybe I'll say, just prove it as for your own reference, no need for me, something like that. Okay, 如果你 not sure. Okay, last question. Recall that a function f is increasing if it's increasing. Show that the set of discontinuous point of any increasing function is countable. 所以这题在问什么这题的图案长怎样？长怎样这个图？这图长怎样 ？You have an increasing function, but you have a discontinuity point, and then you should increase again, discontinuous, increase again, discontinuous, okay, and so on. Right. So what we want you to show is this set here. This continuous point here will form a countable set. Okay, if it is finite, then you are done. But how do you argue that you won't need uncountable index to index it? Yeah. So when you think about countable, right? 你要想属于是 countable 先 relate to the countable set you know. Because everything here is about what? Bijection, injection. Okay, so what are the countable set you know? The question already tell you this is countable. So you need to go and find the countable set. What countable set that you know? Here. Natural number 跟还有什么 rational number. Okay. So if you can make an injection into or bijection into natural or rational, then you are done already. Okay. But in this case here, actually there's an obvious thing you can do. You can find a rational number that attached to them. Do injectively. What? How? Okay. So a lot of you will say that, because the left limit and the right limit is different. Okay. Then there will be a interval around here. you just pick a rational from this interval to every discontinuous point. Why is it an injection? Why all these rational is different? You can pick because it's a density problem here, density argument. But why are they different? They are disjoint. Why are they disjoint? Increasing, good. Yes. So we are using all the assumption here. Okay. So the right limit and the left limit already different. Okay, for the consecutive discontinuity point. Okay, for sure this open interval should be disjoint. Okay, yeah. Okay, good. Last part, show that the set of continuous function has cardinality C. Okay, has cardinality C. How to show this? Okay, so one direction is easier. Okay, you can put real number into, you could have a real number inject into this continuous function here, just by consider x to be the constant function. Fy equals to x, the constant function. The other direction, the other direction a bit tricky. It's a bit tricky, the other direction. Okay, the other direction is a bit tricky here. How to know that continuous function is as large as R? A bit tricky. In fact, we won't show it as large as R. We will put it into R infinity actually. Okay, we will put this CAB into R infinity because we proved in class that the cardinality of R infinity is C. Actually, we proved for ORN. Some of you still repeat the proof inside your assignment. You can repeat, okay, for your onset, no need for me. Okay, you can do it for yourself because we already do in class already. Okay. So instead of putting into this Rn, I will put it into R infinity. Where to find R infinity inside here? Where to find? So what we're gonna do is we just look at the rational point in the interval here, and then what? We look at the f on this set here. So this is the thing inside R infinity here. Okay, so we send an f to the image of R on this. Can or not? 可以吗? Q intersect AB, for sure this set should be countable. So if it's countable, we can enumerate it. We can label them X, Y, and Z. Okay. The point is, why is this injective? Why? Why is it injective? So the key principle here is, so the picture here looks like this. So here got A, B, right? And then maybe you got A1, A2, A3, something like that, right? These are all the rational points. So the point here is, if you know the points on this rational point, actually there's only one way to see f already. 只有一个方法呀，它就是你的那个原来的 f. Why? Why is it true? Because your function is continuous, and then the complement of the rational is what? Irrational number. And then every irrational number is a limit of rational number. Okay, so let me write down first. So let me put an x here. So limit of, let's say, n to infinity of an equals to x. But what is this? If I apply f on both sides, what is this? This is actually the limit of n to infinity of fx, fan. Okay, so if you already know fan here, their sequence also converge to what? Fx. Okay, there's only one way to do it because your function is continuous. Continuous apply here. Okay, here's continuity. Okay, so here tells you that how you join them. You look at the sequence of fan. How to join them? How do you join them? Really coming from how you join the an. Okay, no? Okay. So in this class 啊，有2个挑战，或者在每一个纯数课都有2个挑战。有没有人知道？你们这边全部都是我学生的，有人记得我讲过吗？在纯数课有2个挑战，最大的挑战有2个挑战啊，
找不到女
2个很大的挑战。Two main obstacles, I mean, 2 main challenges. One is about idea. 2, yes, expressing the idea. 2个东西你要学 improve pure math form. Okay, let's say 老师，我有 idea， 我不会写，可以把你 idea 写下来先，写下来先。
会写吗？
I mean 就是写不好的那种写下来 ，OK， 写罢了 ，OK， and then I will correct your idea， correct 到你会写为止。比较惨的是什么？会写，我不知道我自己在写什么，这个我救不了你，我救不了你，真的，我救不了你。你会写，你写很多 proof 出来，你不知道你在做什么，我救不了你，因为你没有想，我不能让你想。对吗？我不能让你想的，你要自己想。你有 idea 不会写，我帮你调，我不会扣你太多分的。如果你 idea 几乎对完了，其实差不多要对完了。所以 idea 重要过 step。有些老师哦，教你抄啊，教你抄 step 啊，sorry is very wrong， 你走不远。你可以在他课走很远，但是你在现实生活走不远。OK， 可能你看到他走很远啊，我也不知道他怎么走这样远。我不知道什么老鼠洞给他爬的，我不知道。但是我们要做好玩的知识、有趣的知识、漂亮的知识，我们一定要知道里面的真谛发生什么事情的，明白吗 ？OK。We need to know what really happened inside the cycle. OK， 虽然你看我只是图给你画啊，我的答案有很多字，你知道吗？明白吗 ？So there are 2 things you need to 可以转换 ，OK， 转换 between these 2 things。OK， 很难，我自己也学了8年，其实 ，OK， 我也学了8年。But 我想告诉你的事情是，已经有人做到了，所以你不要担心，有人做到了。我们一起做 OK 的，我陪你做，我有 office hour，OK 吗 ？So please use it wisely. And then another thing about extension so we will set a deadline right, and then has an extension. So 如果你做不完，你可以 try to 跟我 extend， 但是你就像你讲哦，你不要把它变成一个习惯，一直 extend 的嘛，这是你自己的 self discipline， 你自己要 control 你自己。但是你说哇，我真的不能。那我身为一个老师，我就说啊，你真的不能，我不是让你先过这一次哦，对吧？但是如果你变成借口，那个就是你自己的自律的问题啊，对不对？但是如果不小心哦，可能我家里出什么事情啊，还是我什么啊，我生病啊，我肚子痛啊 ，OK 啊，没有问题啊，1次2次是 OK 的 ，OK， 这种东西我们就 open 一点，但是你不可以一直 induction， 什么叫做 induction？延了又延，延了又延，我怎样做哦？你要引导到 infinity 咩？可以的吗？我们也只有3个月给你引导罢了，你引导超过4个月，我就跟你讲拜拜了，对不对？不可以的吗 ？You understand or not？ 给自己一个期限 ，OK？ 不能来 get help 就这样简单罢了。我也不会强求你什么，你一定要100% originality 也没有这样的事情的啦。但是我就是要求有意要求吧啦，不要抄就对了。用你的理解写下来，不管对还是错，自己的理解写出来，不要抄就对了。OK， 不要100%抄，用自己的理解。第一个你可以做的事情，我们老师很常教我们吧 ，paraphrase 啊，第一个做的事情是 paraphrase 先，把那些符号换掉啊。字可能排列换掉啊 ，something like that。因为你在做这件事情的时候，其实你就是在问自己啊，这个东西是什么啊？我可以换吗？你就是在慢慢理解了啦，不然对不对啊？ 不要好像说理解跟不理解是零和一的问题，不是，好不好？这个不是二元对立的东西，你一定是在中间的 confuse 的，会，看哦，明白吗？有没有 sense？OK，可能有人要进来上课，see you next week。
来讨论看。